So what we use to record earthquakes are called seismographs. So a seismograph is an instrument that's going to record the motion of the earthquake that's happening on the ground. I'm sure you've seen seismographs in some really cheesy movies, right, where there's an earthquake that happens, and then you see the pen move around up and down. But there's actually two different types of seismographs. So the one over here on the left is a vertical motion seismograph. This records the up and down movement that occurs. The one over here on the right is a horizontal motion, and this records back and forth motion. So really, a lot of seismographs, a lot of places where there's a lot of seismic activity, we're going to put both types of seismographs, because as we've learned, right, we have different types of motion inside the Earth with our P waves and our S waves, so they're going to record different information. So the seismogram itself is the actual sheet of paper that is containing all of the information. So as we've learned, right, what the seismograph is really doing is it's recording the P waves, the S waves, the love waves, and the Rayleigh waves. So remember, the first waves that come in are always our P waves, right? And so they're the first to arrive, always, every single time. Then next, we get our S waves, and then we get our surface waves last. And they're a little bit different to tell where our love waves and our Rayleigh waves are, but for the sake of trying to figure out where the epicenter of an earthquake is, we're not really too worried about the surface waves. We're mostly worried about our P waves and our S waves, because these are going to tell us where our earthquakes occur. So as I said, right, what they do is they measure the wave arrival, right? So, and what's really interesting about this is when you're measuring the wave arrival, right, if your P wave, right, comes in and it's really small, right, and it keeps going, that's telling you something about the magnitude of the earthquake. So either you're really far away from the earthquake and the energy has dissipated, or you're close to the earthquake and it's not very big. So the size of the actual shaking tells you a little bit about the actual earthquake itself. Now, we can also take a look at whether the line goes up or if it goes down. Okay. So if the line goes up or down, it's going to tell you about the first motion. Okay. So what we're seeing here is when the pen goes up and down, it's telling us as that P wave passes through the rock, whether it's physically pushing against the rock or pulling against the rock. So these little squiggle marks actually give us quite a lot of information. So as we've already discussed, our P waves always arrive first, without question, and then our S waves arrive second. However, there's going to be a time gap in between them. And the amount of time that's in between when those two waves arrive is going to be directly correlated to how far away you are from the earthquake. So what this is this is actually one of those really horrible math problems that we all really hated. So if you think back to those math problems where you have, right, one train leaving the station at 50 miles an hour, another train leaving the station at 60 miles an hour, right, you want to figure out how big the gap is 10 miles down the road, right? We all hated those kind of questions. But in general, we can say, right, as those trains are leaving the station, for a while it's going to look like they're going the same speed. The further and further you get down the road, right, the train that's going faster is increasing the gap in between the two trains. And that's exactly what happens here. So the closer you are to the epicenter, the smaller the time interval, right, between when the P wave arrives versus the S wave. Now, the further away you are, however, right, from the epicenter, there's going to be a really big time interval between the P wave arrival and the S wave arrival. Now, because our continent is pretty much always made up of granite and our ocean is always made up of basalt, these P waves and S waves pretty much travel at about the same speed all the time, right? So your P wave is going to travel at some given speed, and your S wave on average is going to travel at some other given speed. So because we know those speeds, we can physically measure the time delay, right, between these two waves, and it's going to tell us the actual distance. So let's take a look at how we do that. So once we figure out this time distance, and the way we do it, and the book is not really good at explaining this, is there's actually a time travel curve. And actually, the next slide is the time travel curve. So let's go ahead and take a look at that, and we're going to come back to finding the epicenter. So the way this works, right, is let's say we noticed that our time interval between the P wave arrival and the S wave arrival was, let's say, 4 minutes or something of that nature, right? 3-4 minutes. So what you do is we're going to measure this distance. So this graph is kind of tricky. So the way it works is different than any other graph. So this distance right here represents a gap of 5 minutes. So what you would do is you would take a ruler and measure that and then see wherever it's the same, right, on here. So it's not like you're reading over and then down. What you're essentially doing is you're taking a look at this much space, say for 5 minutes, and you're trying to figure out where does that fit on here. Right? So you would take a ruler and kind of see where it physically fits. So once you do that, then you can read down to the distance. So let's say here we've got this station with its time gap. The P wave arrived at 4 minutes 6 seconds. The S wave arrived at 7 minutes 25 seconds. We have our time gap interval. Right, we measure that on here, we measure it over here, and we read down, and it's 2,000 miles away. So we know station 1 is 2,000 miles away from the epicenter. And you can see we can do the same thing with station 2 and station 3, right? We figure out the time gap, we read down, we see it's a 4,000 mile distance and a 6,000 mile difference. Now, the issue here is when we take a look at this, if I know that I am 2,000 miles away, does it tell me which direction? Right? Well, the answer is no, right? I don't know. It could be in any direction. So what this is really giving me is a radius. So let's go back and take a look here. So now what we can do is we can actually plot those by using a compass. So all of your maps have a key on them, like you can see here. So if I know that first station was 2,000 kilometers away from the epicenter, I can scale my radius here to be 2,000 kilometers, and I can draw a circle with that radius. Right, then I will go to station 2, do the same thing for 4,000 kilometers. Station 3, do the same thing for 6,000 kilometers. And what you see is they all intersect on one point. And it's that one point that is determined as the epicenter. So figuring out the epicenter is actually, surprisingly, quite easy.